Hello and welcome back. In this video, we're going to go through coming up with the equation of a sphere in 3 dimensions. So this is the analog or extension of the 2-dimensional circle, and now take that to 3 dimensions. So we're going to see parallels, just like we did with the distance formula in 3 dimensions compared to the distance formula in 2 dimensions. We're going to see another parallel between circles and spheres as we move up a dimension. So what I really would like to start with here, by the way, at the end of this video we are going to sketch a sphere, but what I'd like to start with is just what's the equation of a circle. So we're just going to go back to 2 dimensions for a second and refresh our memory on how we came up with the equation for a circle. Maybe you could find the equation of a circle and just write it down. That's great. But if you don't remember the equation of a circle, that's even better, because I want to stress I'm not so concerned with you memorizing equations. Sure, you can do that, memorize things. What I'd rather have you do is understand where that equation comes from, why it is the way it is, because this is going to help us tremendously as we go through the course. So again, this is something you have to do intentionally, is instead of just memorizing and copying down, think about why something is true. So we're going to jump back to 2 dimensions here, and here's a little problem. Maybe you've encountered in a geometry class or in a Calc 1 class, something like this. Find an equation of a circle, or at a pre-calculus class even. Equation of a circle centered at 3, 2 with radius 2. So one thing I'll do to start this is just draw what that circle looks like. You know what, I'm going to actually extend this. I wanted this to be a little bit bigger. How about 1, 2, 3. So there's 3 and a y value of 2. 1, 2. So the center of my circle is right here. And I want the equation of the circle. So again, think about what is a circle. A circle is the set of points which are the same distance from the center, that distance being the radius. So what I want here is the set of points. I want the set of points that are distance 2 from the point 3, 2. That's what I'm interested in. That's how I want to rephrase this, because this is how we're going to generalize to 3 dimensions. The idea is distance, and that's why there's such a parallel between the distance formula and the equation of a circle. Right, so set of points that are distance 2 from 3, 2. So 1, I want to go down. That's 2 away. So this point is on the circle. That's distance 2 from the center. This point is on the circle. If I go up 2, I've sort of drawn myself into a corner here. The top would be up here. This would be at 1, 2, 3, 4. I have to extend that a little bit. Apologies. And then 2 over this way. So 1, 2. So those 4 points are all on the circle. And so my circle looks like everything that's distance 2 from that center point. Let's try that again. So again, it's not going to look beautiful. This is part of why I like math, because I can describe what the circle is. The drawing is a little sort of secondary for visualization purposes. So there's the circle. What's the equation of this? So again, it comes from what is the set of points that are distance 2 from 3, 2. So if I say, let's say xy is an arbitrary point, I'm going to let it be an arbitrary point on this circle. The circle I've described here. Then its distance from 3, 2 has to be equal to 2. So then distance from 3, 2 to xy is 2. So what's the distance from 3, 2 to xy? Well, we know the distance formula in 2 dimensions. That looks like the difference in the x values, so let's say x minus 3 squared, plus the difference in the y values, y minus 2 squared, and that distance has to be equal to 2. And so this is the equation of our circle. Now, oftentimes we don't like the square root hanging out in our equation. More on that later. We don't want the square root hanging out. And so what I'll tend to do here is bring the square over to the other side. So I'll write this like x minus 3 squared plus y minus 2 squared equal to 2 squared, which is 4. So maybe now this is refreshing your memory a little bit, recalling what the equation of a circle is in general with radius r. So we want the distance between an arbitrary point xy and AB to have distance r. So the distance between xy and AB is going to look like x minus a squared plus y minus b squared, and I want that equal to r. So that works. That's a good equation, but typically we'll move that square root over. We'll square both sides of it. Looks a little bit nicer. Don't have the square root hanging out, and there's our general equation of a circle in R2. This comes, the reason why we went back to 2 dimensions, the reason why we're rediscovering this equation of the circle is so that we can generalize it. Now that we have a distance in 3 dimensions, we can now take that and come up with the equation of a sphere, because a sphere is the 3-dimensional analog of a circle. It's the set of points in space that are the same distance from some center point. So if we just start with, let's say, 0, 0, 0, if we want the origin to be the center of sphere of radius r, we want the set of points that are distance r from that. And so what that looks like, what's the distance? So again, I'm going to start with an arbitrary point on the sphere. Let x, y, z be on the sphere, an arbitrary point on the sphere. Then the distance between x, y, and z and 0, 0, 0 needs to be equal to r. So the distance, let's see, distance from this arbitrary point, anything on the sphere, to 0, 0, 0 is r. So what's the distance between x, y, z and 0, 0, 0? Well, that distance looks like x minus 0 squared, so that's just x squared, y minus 0 squared, that's y squared, plus z squared is equal to r. And again, we're going to square both sides and write it like this. X squared plus y squared plus z squared is equal to r squared. And so there is a equation of a sphere of any radius you want that's centered at the origin. Looks like this. So just pick a radius r, and that gives you a sphere centered at the origin. What if we want to be centered somewhere else? Well, again, we're going to go to the distance in 3 dimensions. So given an arbitrary point, x, y, z is on the sphere. And we want the distance from that arbitrary point to the point A, B, C, or I'll just say is r. So what's the distance between those 2 points? That's where our distance in 3 dimensions comes from. It's square root of x minus a squared plus y minus b squared plus z minus c squared. We want that to be equal to r. Great, we're almost there. All I'm going to do is square both sides. Again, this part isn't that important. This is more for aesthetics. We square both sides and obtain the following equation: x minus a squared plus y minus b squared plus z minus c squared equal to r squared. There's our equation. Any point x, y, and z satisfying this equation for a particular a, b, and c and r gives me a sphere. So what does that sphere actually look like? Well, we're going to plot one. So in this problem, we're going to give an equation of this sphere, specified sphere, with the specified radius, and then we're also going to sketch it. So here's x, positive y, positive z. The point 1, 1, 0, I'll start by plotting that. So let's say 1, 1, 1, 1, 1, 1. Let's redo that one. I want it to be basically the same. I want it to form a square. 1, 1, 1. So there's 0.3. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 3, -3, -3. Nope, sorry. +3 and -3 over here. So first I'm going to start by sketching 1, 1, 0. That's 1 in the x direction, 1 in the y direction. Z value of 0. So here's 1, 1, 0. Here's our center. And now I want the collection of all points in space that are distance 2 from this point. So when I did this for the circle, we went in the x direction positively and negatively, and then the y direction positively and negatively. Here we're going to do that 3 times. So let's see. X direction, I can go over 2, so that means I can go all the way down to 3 here. So this is sort of my, let me do this in blue. 1, 2. This is the extent in the x direction that the sphere goes. That wasn't quite what I wanted. There, that's a little bit. So that's the extent in the x direction. I'm going to travel in the negative x direction 2 units. There's the extent there. In the y direction, I'll use green for this. 1, 2 over. 1, 2 over. That would be here. And then in the z direction, also 2. I'll use a third color for this. How about red? So we want to go up 2 units. There's the extent there, and down 2 units. So there's the extent down there. And one way a sphere generalizes a circle is that we actually have 3 circles which define a sphere. So what I mean by that is this. Let's see. So I'm going to draw a circle in the xy plane, distance 2. So that means I'm going to come out to this extent here. Let me start this way. Come around like this. And this stuff is going to be, let me try that one more time because I want to do dotted lines for things that are going to be behind the sphere that I'm not going to be able to see. So that's going to start right here. It's going to look a little bit wonky because we're drawing in perspective. So it takes a little bit of practice. Again, I'm not perfect. So there's the slice. We haven't drawn the sphere yet, but if you imagine the sphere that's going to be here, this is, if I take the xy plane and I slice it, I'm going to get a circle that looks like this. This is going to be visible, so I don't want dotted lines there. We'll do solid lines there. So I have that one. I also have a circle if I take the xz plane, or a plane parallel to the xz plane that goes through the center, and I slice it, I'm going to get a figure that looks like this. I'm going to get a circle. Again, it's going to come up. So this is coming at us and going away from us. So this point now is going to be dotted. Dotted. And there's a circle parallel to the xz plane. Again, it's not perfect. I hope you're getting the idea from it. And then we also have one other circle if I intersect the sphere with a plane parallel to the YZ plane. That's going to look like this. I'm going to be able to actually see all of this one. Can you visualize that? Now it takes a second. Red one's coming at us and away from us. Green one is sort of flush with us to the left and the right and up and down. And then the blue one is sort of the one parallel to the floor of the sphere. And so that is, so if you imagine all the points kind of fill in that shell, you get the sphere. I can't really shade it in. Things are going to get really messy if I start shading it in, but nevertheless, that is the sphere. What's my equation for this? Well, any point on the sphere is distance 2 from 1, 1, 0. So if I remember that, I think distance formula, I want x minus 1 squared plus y minus 1 squared plus z minus 0 squared to be equal to 2 squared, or 4. So there's my equation, and there's my sketch of the sphere. So definitely practice sketching it. Again, it doesn't have to be perfect, but remember these things that I've been telling you about. Make sure things are parallel to what they need to be parallel to. Any lines moving in the x direction or y direction, make sure you're parallel to the x-axis. That's why I went like this, right? That's how we got this one. Or if I'm parallel to the y-axis, make sure you're actually parallel to the y-axis. And same thing for z. And that's our sphere. So pretty cool. And then a little note here about the difference between balls and spheres. So a sphere is what we just pointed. It's the points that are exactly distance r from the center. That is what this equation looks like. This is what we've been talking about the whole time in the video. Equal to r squared. Just the ones that are exactly that distance from my center. That is a surface in 3 dimensions. It's a 2-dimensional object, a surface, sitting in 3 dimensions. That's the sphere. A sphere is the surface of a ball. So if you take that sphere and you fill everything in, so back to this drawing, if you fill this all in, everything inside that volume, now we're talking about what's called a ball. And we don't just want the points that are exactly that distance from the center. We want the points that are at most that distance. And that's why we have a less than or equal to for the ball. If I have a, let's say, greater than or equal to symbol here, that would be the points that are distance further than r. And so it would be the outside of the ball. But less than or equal to gives us the inside of the ball, right? If I pick a point like this that's in the xy plane, the distance is not 2 to the center, but it is less than 2. And so what that means, it's inside the ball. That's the idea. That's the same thing back here to the, if I go to 2 dimensions again real quick. Instead of a circle, if I want a disk, so the 2D analog of a ball is a disk. And that's the stuff that's inside of a circle. So that's all of this jazz that's inside the circle. If I want all of those points, so that's now a 2D object sitting inside of 2 dimensions. If I want that, I don't want equal to 2. I want anything that's at most distance 2. And so instead, I would get equation of the disk would be square root of x minus 3 squared plus y minus 2 squared less than or equal to 2 would give me this disk. That's the same thing going on with the sphere versus the ball. Replace that equality with an inequality. And remember where the formula comes from. And that'll tell you whether it should be less than or equal to or greater than or equal to. That's it for this video. I'll see you next time.